This is an Algebra 2 lesson, and today we're going to look at logarithms as inverse functions and the graphs of logarithm functions. So to remember how to find inverse functions, we need to look at this first. To find an inverse function, we need to switch the variables x and y and then solve for y. And when we find an inverse, we know that the domains and ranges will switch as well. We also need to remember that log base b of x equal to y is the same as b to the y equals x. Okay, so let's start with our first example. We first want to start by listing the domain and range of the function given. This is an exponential function. We know that the domain is all real numbers. The range of an exponential function is dependent on the value of the horizontal asymptote. Our horizontal asymptote here is at y equals 2, so the range is going to be y greater than 2. Now, to find the inverse, we're going to switch our variables x and y. So we have x equals 3 to the power of y plus 2. In order to solve this for y, we need to get the term that has the y in it by itself on one side of the equation. So subtract 2 from both sides. We get x minus 2 equals 3 to the y. And now we're going to use our properties here of how to write exponential equations as log equations, that b raised to the power of y is equal to x. So here's our b raised to the power of y equals x minus 2. That's the same as log base b of x equals y. So this is the same as log, our base is 3, of x minus 2 is equal to y. For inverse functions, domain and ranges switch. So now our domain is x greater than 2. Our range is all real numbers. Notice that when x is greater than 2, this expression is greater than 0, and this is always going to be the case for the logarithm graph or the logarithm function. Okay, our next one is y equals e to the x minus 1. Again, it's an exponential, so domain is all real numbers, and the range is tied to the horizontal asymptote. Our horizontal asymptote here is y equals 0, so our range is y greater than 0. Inverse. Let's switch x and y. We get x equals e raised to the power of y minus 1. The term y minus 1 is an exponent with a base of e. So we are ready to write it, go from exponential form to log form. This time we have log base e of x equal to our exponent of y minus 1. Solving for y by adding 1 to both sides, we get y equals log base e of x plus 1. Okay, the plus 1 is outside or done after the log. Now, when we have log base e, that's our base of a natural base, so we frequently write it using ln, or log natural of x plus 1 is equal to y. Domain, this is switches from our exponential, so our domain is going to be x greater than 0 instead of y greater than 0. Our range is going to be all real numbers. Now let's take a look at starting with a log function and going back to an exponential function. We're going to start as we always start by getting the term that has the x in it by itself. Actually, we're going to switch the variables first, and then we're going to get the term with the variable by itself. So we're going to write x equals log base 2 of y minus 3. We want this term with the y by itself, so add 3 to both sides. We get x plus 3 equals log base 2 of y. And now we're going to make use of our property here. I can switch it from log form to exponential form by taking the base to the exponent equal to the argument. So our base is 2 raised to the x plus 3 is equal to y. We didn't find the domain and range of the original like we were supposed to, so let's go back and look at the domain and range of our function. This is a log function, and I know that this part right here has to be greater than 0. So we have a domain of x greater than 0. And our range, just like we found up in questions 1 and 2, the range of the log functions are all real numbers. Okay, so now our domain and range for our inverse. It's an exponential function. I know the domain is all real numbers, which is the same as the range of our log function. And our range this time is y greater than 0. Our horizontal asymptote for this exponential function is y equals 0, so our range is y greater than 0. And it's the equivalent to our domain of our log function. Okay. Number 4, let's go ahead and find the domain and range of our log function. Our domain, the expression that we apply the log to, this x minus 1, has to be positive. So x minus 1 has to be greater than 0. So x has to be greater than 1. And the range is going to be all real numbers. Now to find the inverse, we switch x and y. So we have x equals log natural, or natural log of y minus 1. We need to get to the y, so we need to undo our log. We need to rewrite this then in exponential form. Our base is e, so e raised to the x is equal to y minus 1. Adding 1 to both sides, we get y equals e to the power of x, and then plus 1. Our domain, all real numbers, as it's exponential. It's also equivalent to the range of the log function. And range, our horizontal asymptote is y equals 1, so it's y greater than 1, corresponding to our domain of our log function of x greater than 1. Okay, so we have some examples now of some applications. In these applications, it's this one happens to be the magnitude of an earthquake. This scale is based on a logarithm scale. It's one of many applications that use logarithm scales. In this case, the energy magnitude m of an earthquake can be modeled by m equals 0.29 times the natural log of E, the energy, minus 9.9. We want to find the magnitude of an earthquake that is generated, that generates 2.5 times 10 to the 24th ergs of energy. So we're going to substitute that in for E right here. We're going to get m equal to 0.29 times the natural log of 2.5 times 10 to the 24th, and then minus 9.9. So we can do that on our calculator. Okay, I had to clear my screen. We're just going to enter that in. We have 0.29, and then we have the natural log. We have 2.5 times 10 raised to the power of 24, and then I'm going to subtract 9.9. And my answer there is 6.39. 6.39, or about a magnitude of 6.4. Okay. Now our second part here, we want to know how much energy is released in an earthquake of magnitude 8. So we're going to put 8 in for m. So 8 equals 0.29 times the natural log of the energy minus 9.9. we need to solve this for e, so we need to go through and do the opposite of our order of operations, which means we need to undo subtraction first. So we're going to add 9.9 to both sides. Get 17.9 equals 0.29 times the natural log of e. We undo multiplication by division, so we're going to take 17.9 and divide by 0.29. And that's going to get us 61.72. It's equal to the natural log of e. Now we need to undo this logarithm, which means we want to write it in exponential form. Our base here is e, so e raised to the power of 61.72 is equal to the energy released. And when we put that in our calculator, we do e to the power of 61.72, and we get 6.38 times 10 to the 26 ergs of energy. 6.38 times 10 to the 26 ergs of energy. Notice that it is 2 orders of magnitude greater than the amount of energy released when we had an earthquake of magnitude about 6. And that's how a logarithm scale works. Okay, our second part is to do graphs of log functions. We're going to start by looking at the graph of an exponential, and remember that's the inverse of a log function, so let's just quickly do that. On an exponential function, remember our domain is all real numbers, and the range is y greater than 0 for our parent function. We're going to graph a few points on our exponential. 2 to the negative 1 is 1/2, 2 to the 0 is 1, 2 to the first is 2, and 2 to the second is 4. So we have this graph. Here's our x and our y. Negative 1, 1/2, 0, 1, 1, 2, and 2, 4. Our exponential function. Okay. When we do an inverse, we switch x and y. So I'm just going to switch these values. My domain is going to be x greater than 0. My range is going to be all real numbers. We switched our domain and range. We're also switching the x and y coordinates. So when x is 1/2, y is negative 1, and we have 1, 0, 2, 1, and 4, 2. All of our values for x, notice, are powers of 2, which gives us nice integer values for y. Okay, so let's graph those. I'm going to use a different color. When x is 1/2, y is negative 1, then we have 1, 0, 2, 1, and 4, 2. Our graph goes this direction. Remember that inverse functions have the line y equals x as a line of symmetry. We can see that line y equals x is our line of symmetry. Notice that our horizontal asymptote on the exponential graph of y equals 0 becomes a vertical asymptote on the log graph. It has a vertical asymptote of x equals 0. Okay? So now let's take a look at another graph with a log without doing the exponential first, so we don't have to work so hard. We're going to choose values for x that are going to be powers of the base. So when we graph y equals log base 4 of x, we're going to choose values for x that are going to be powers of 4. So I'm going to start with 1/4, and then I'm going to have 1 and 4 and 16. Okay? Remember, 1/4 is 4 to the negative 1. So this is going to be negative 1. This is log base 4 of 1/4. We get that with a power of exponent negative 1. Okay, so we have 4 to the negative 1 is 1/4. So we know that log base 4 of 1/4 is negative 1. That's how we got negative 1 here. Okay, we're going to do the same thing here. When we have 1, we have to think 4 to what power is 1, and that's going to be 0. We put 4 in for x. We have to think we have log base 4 of 4. We have to think 4 to what power gives us 4. That's 1. And here we're thinking 4 to what power gives us 16, which is 2. So let's take a look at that graph. Domain first. Our values x here have to be positive, and our range is going to be all real numbers. Okay. Remember, that's the switch, or the switching the domain and range for an exponential. Since x is greater than 0, I'm going to put my x-axis way over here, or my y-axis way over here. Here's my x. And I'm going to graph 1/4 negative 1. That's snugged up right here. 1, 0, 4, 1. 16, 2 is way off here somewhere, so our graph is going to be snugged up next to the y-axis, and then it's going to come out here and be very flat, not quite horizontal, because eventually I'm going to get up to 2 by the time I get to 16, but it is very steep. Vertically very steep, horizontally very shallow, very close to 0. Okay, so now what I want to do is I'm going to use transformations to get this graph, log base 4 of x minus 2 plus 3. It's a transformation of the graph that we just did. All it does is it shifts us 2 units to the right and 3 units up. So let's take each of our points and move them 2 right and 3 up. Okay, so 2 to the right and 1, 2, 3 up. 2 to the right and 1, 2, 3 up. 2 to the right and 3 up. Now, our vertical asymptote, remember this graph, our parent function, our graph snugged right up next to x equals 0. Since it's going to be moved 2 to the right, we're now going to be snugged up next to x equals 2. This is going to be our vertical asymptote. Okay, so I'm going to draw that graph, drawing it close to x equals 2 here. It's going to come and curve and get very flat. And that's our graph using our transformations. So those are graphs of log functions.